All right, our last trig sub example. We're supposed to integrate 3 divided by the square root of 3x squared minus 6 cubed. How would you know this is a trig sub example? Because you see this square root sign with the different terms underneath the radical. It's almost x squared minus some number. You just have this coefficient here kind of getting in the way. Because of the coefficient on the x squared, we're going to have this kind of part 0 that we saw in the previous video, where we factor out a 3 from each of these terms. Instead of thinking about the radical as the square root of 3x squared minus 6 cubed, we're going to think about the radical as the square root of 3 times x squared minus 2 cubed. Don't let this extra cubed throw you off. All we're doing is factoring out a 3 from each of these terms, which produces this 3 right here, so that what we'll end up with left underneath the radical will fit one of our different forms. Underneath the radical, we have something times something. So because we can distribute exponents over multiple factors, not over multiple terms, not over pluses and minuses, but over multiplication, we can rewrite this as the square root of 3 cubed times the square root of x squared minus 2 cubed. It's pretty complicated algebra, but it's consistent. It's almost the same thing that we did up here. We had a coefficient on the x term, so we had to factor it out in front, so that what we were left with underneath the radical fits one of our 3 trig sub forms. Note that this time it's not a number minus x squared, nor is it a number plus x squared. It's x squared minus some number. So now we're in this third case here. I've got this 3 up on the top, which is just a coefficient, so I can pull that out in front of my integral sign. And then down in the denominator, instead of the square root of 3x squared minus 6 cubed, I have the square root of 3 cubed times the square root of x squared minus 2 cubed. But the square root of 3 cubed is just the square root of 27, which is itself just a constant, so I can pull that out in front of my integral sign as well. All that's left behind is a 1 up on the top and the square root of x squared minus 2 cubed. If it's easier for you to see the steps, instead of writing the cubed underneath the radical, we can make the radical cubed. Because taking the square root of something is just the same as raising it to the 1/2 power, and x squared minus 2 to the 1/2 power cubed is the exact same as x squared minus 2 cubed to the 1/2 power, because in either instance we multiply together these two exponents and get x squared minus 2 raised up to the 3/2 power. Some exponent rules coming into play here. Anyways, now that we've cleaned things up sufficiently, we can do our trig substitution. We got the square root of x squared minus 2. That's the same as the square root of x squared minus a squared, where playing the role of the a squared is a 2. If a squared is a 2, then a is the square root of 2, so x is equal to the square root of 2 times secant of theta. Most books would start you out right here, although I'd argue that if you divide both sides by root 2 and then take the arcsecant of both sides, you'd see that theta is equal to the arcsecant of x over root 2, and even though these two equations are completely equivalent, sometimes it's useful to write them both. The one without the inverse trig functions is the one we're going to want to take derivatives of, so I got dx is equal to root 2 times the derivative of secant of theta. The derivative of secant is secant times tangent, so I get secant theta tangent theta d theta. It's ugly, but I have all the pieces necessary to substitute in here. On the top of my fraction, I still got a 1. On the bottom of my fraction, there's something cubed. That something is the square root of something. Underneath the radical, I got x squared minus 2, but playing the role of the x is root 2 secant of theta. So I got root 2 secant theta squared minus 2. Don't forget to also substitute for the dx. dx is equal to root 2 secant of theta, tangent of theta, d theta. This is that step where it kind of blows up and it looks really overwhelming, but what you'll see is things work out really nicely. Instead of having such a long expression, I'm going to put all this stuff up on the top of the fraction, and I'm going to recognize that the square root of 2 is just a constant, so I can pull that out in front. So I got 3 root 2 divided by the square root of 27 times the integral of, up top I got secant theta times tangent theta, and then I still have my d theta off to the side here. Down on the bottom I got something cubed. That something is the square root of something squared minus 2. If I square that something, root 2 secant of theta squared, I get 2 secant squared theta minus 2. Note that the constant term, 2, is the exact same as the coefficient on my secant squared term. It's not a coincidence. That always happens. I factor out that 2, and I got the square root of 2 times secant squared theta minus 1. I still have 2 terms underneath the radical, secant squared theta minus 1, but I bet you I can change that into a single term by using my Pythagorean identity. Let's go back to our 3 different variants of the Pythagorean identity. Here's the one that has a secant squared in it. If you subtract 1 from both sides of the equation, you get that tangent squared theta is equal to secant squared theta minus 1. So instead of writing secant squared theta minus 1, I can write tangent squared theta. I still have the same ugly coefficient out in front, 3 root 2 divided by the square root of 27. On the top of the fraction being integrated, I still got secant theta, tangent theta. I still have my d theta, which I forgot to write, hanging out here to the side. I still got something cubed down in the bottom, but instead of that something being the square root of 2 times secant squared theta minus 1, I can think about it as the square root of 2 tangent squared theta. Because again, secant squared theta minus 1 is tangent squared theta. Doesn't look like a big difference from here to here, but it's a huge difference because what's underneath the radical no longer has 2 terms. It just has 1 term, so we can cancel out the square root sign, which remember is our goal all along. Instead of the square root of 2 tangent squared theta, I can write the square root of 2 times tangent of theta. The square root hits the 2 and the square root hits the tangent squared theta, but the square and the square root cancel out. Technically, there should be absolute value symbols, but we never need to worry about those. Good news, the square root is gone. We're done with part 1. And you're like, oh my God, we still have 2 more parts to do? Well, it'll turn out we kind of don't, because look what happens when I simplify this a little bit. This root 2 is just a constant. So this root 2 cubed can be brought out in front here. So I still have the 3 root 2 up top and the square root of 27 down on the bottom. But since 2 cubed is 8, I can write the square root of 8 down here. All that leaves in my integrand is secant of theta, tangent of theta, divided by tangent cubed theta. Wait a minute, you got tangent up on the top and 3 tangents down on the bottom. Could you cancel something out here? Yeah, absolutely you could. Turns out we can simplify this mess a little bit too, but maybe I'll wait to simplify that. And for now, just leave it as a huge expression. I'm focused more on the integration part, so really I'm focused on simplifying what's in my integrand here. This tangent's gone, one of these tangents is gone, so I'm left with secant of theta divided by tangent squared theta d theta. Is that something you can integrate? Hell yeah it is. You know how I know that? Because it's the exact same thing we had in the previous example. Secant of theta over tangent squared theta. It's surprising because this problem looks nothing like this problem down here, but because of the interconnectedness of all our different trig functions and the relative scarcity of trig expressions that we're able to integrate, there's only so many different expressions that you can come up with here. And the one we have right here is identical to the one we ended up with up here. So we'd integrate it in the exact same way as we did here. The only difference is up here, our coefficient was 1 over 4 root 2, whereas down here, it's this huge mess. So maybe I can simplify this huge mess a little bit. I got 3 root 2 up top, and then instead of the square root of 27, I can think about that as the square root of 9 times the square root of 3. In other words, 3 root 3. And then instead of the square root of 8, I can think about that as the square root of 2 times the square root of 4. In other words, 4 root 2. And by factoring out those perfect squares, I'm able to cancel out all sorts of stuff. This 3's gone, this 3's gone, this root 2's gone, this root 2's gone. So I'm left with just 1 divided by 4 root 3. Or if you're the type that likes to rationalize stuff, root 3 divided by 12. If you multiply the top and the bottom by the square root of 3. Really, I'm not super worried about the coefficient. What I'm worried about is what goes inside these parentheses. And what goes inside these parentheses is the antiderivative of secant of theta divided by tangent squared theta, which as we saw above is the antiderivative of cosine of theta divided by sine squared theta, which as we saw over here is just negative cosecant of theta, which I can write inside these parentheses, or these parentheses, or these parentheses. The point is I'm all done integrating. I got negative root 3 over 12 cosecant of theta, technically plus c. I'm not done at this stage. I need to change my variables back and simplify. I still need to do part 3 here. So remember, theta was something that we created in this problem. It's equal to the arcsecant of x divided by the square root of 2. So really our answer is negative root 3 over 12 times the cosecant of the arcsecant of x over 2, which is a great answer in that it involves the variable x instead of the variable theta, but it's not a perfect answer because it can be simplified because we have an inverse trig function inside of a trig function. So off here to the side, maybe we simplify the cosecant of the arcsecant of x over 2. The way we do that is this substitution. We let theta be equal to the arcsecant of x over 2, in which case the secant of theta is equal to x over 2, which defines a right triangle that we can draw. Put theta down here in the corner. Secant is the reciprocal of cosine. Using SOHCAHTOA, we know cosine gives us the length adjacent divided by the hypotenuse. Therefore, secant gives us the hypotenuse divided by the length adjacent. So this is x and this is 2. If I know two sides of a right triangle, I really know all three of them. I don't know, maybe you'd call this one b or something and say that a squared plus b squared equals c squared, and then solve the equation for b. You get b squared equals x squared minus 4, and therefore b is equal to the square root of x squared minus 4. Now that I know all three side lengths in this triangle, I can come up with a simplified version of the cosecant of the arcsecant of x over 2. Because the arcsecant of x over 2 is really just this angle theta. So this is really just the cosecant of theta. And the cosecant of theta from this triangle and the fact that cosecant is the reciprocal of sine, I think SOHCAHTOA, sine is opposite divided by hypotenuse. Therefore, cosecant is hypotenuse divided by opposite. It's x divided by the square root of x squared minus 4. That's my answer. No, that's a simplified version of the cosecant of the arcsecant of x over 2. My answer is down here in pink, which I can now simplify if I change the cosecant of the arcsecant of x over 2 into this expression. I get negative root 3 over 12 times x divided by the square root of x squared minus 4 plus c. Wow. The calculus in these problems is hard, but really I think the biggest hurdle in these problems is the trig. There's some expert level trig going on to be able to do these problems. And frankly, that trig is beyond the grasp of most students. If you're able to follow this, you should be really proud of yourself. And if you're not, don't be too hard on yourself. It's really testing knowledge from a previous class more than it's testing your calculus knowledge.